Assalamualaikum warahmatullahi and good morning. So for today we will look at lesson 17, which is in lesson 17 kita akan cover 11.1 and 11.2. So from the first subtopic 11.1, so kita ada 4 learning outcome. So first one, define and use mass defect. Next, define and use binding energy. Then we will look at how to determine the binding energy per nucleon. EB/A. A is number of nucleon. And the last one is sketch and describe graph of binding energy per nucleon against nucleon number. Okay, then from the second subtopic, kita ada 5 learning outcome. Explain alpha, beta plus, beta minus and gamma decay. Next, we state and use decay law. So decay law is dN over dt equal to negative lambda n. Then in our third learning outcome from 11.2 is define and determine activity A and decay constant. So this is the symbol for decay constant, alpha, wavelength, lambda. Next, use n equal to n naught, exponent negative lambda t. So lambda is the decay constant and A equal to A naught, exponent negative lambda t. And the last one is define and use half-life t. Half-life equal to ln 2 over lambda. Okay, before we go further, let's look at the particle properties. So this is the particle property yang you akan biasa tengok. So proton P11, electron E0 negative 1, neutron N10, hydrogen H11. So kita ada juga unit conversion from 1U equal to 1.66 exponent negative 27 kg. 1 EV stand for electron volt, equal to 1.6 exponent negative 19. And the third one is the relationship between C square. So C ni actually that is the speed of light. Speed of light square equal to 931.5 MeV. M is mega. Mega 10 to the power of 12. Then the overview lah ya. Okay, so let's look at the properties of nucleus. So mana satu nucleus? Nucleus yang tengah-tengah ni, nucleus. So actually nucleus ni contain, we have proton and neutron dalam nucleus. Nampak yang blue colours, that is the neutron, and proton yang black colour tu. So combination of proton and neutron tu actually that is the nucleon ataupun that is the nucleus. Elektron ni yang luar-luar ni lah. This is the electron. Okay. Okay, our first learning outcome is to define and use mass defect. So definition of mass defect, the difference between sum of masses individual nucleon, individual. So okay, how many electron and how many proton and neutron dalam nucleus tu, kita tambah-tambahkan dia. Then difference between the mass of the nucleus tu sendiri. Okay, so unit dia ada dua, satu dalam AMU or U, and one more is in kg. So actually we have two formula to find the mass defect. So first is ZMP plus NMN minus mass of nucleus. So dia boleh bagi dua situation. Sama ada we can use the mass of nucleus. So nucleus ni yang mana? So nucleus ni ingat balik. So nucleus is actually the combination of neutron dengan proton. Neutron and proton tu yang duduk dalam nucleus. Okay, so the second one is delta M. So still there is delta M stand for mass defect. So mass defect equal to ZMH. So mass of hydrogen plus NMN, mass of nucleon, mass of neutron minus dengan mass of atom. So let's say question to us to find the mass defect, tapi yang given is the mass of atom. So atom tu yang mana? The whole, which is they consist of nucleus and the other electron. So kita guna the second equation. Okay, so let's say we have an example. So the nucleus kita ada helium nucleus. We have 2 neutron and 2 proton. So the mass of the nucleus kita 4.001503 AU. Okay, this is the mass of nucleus. Okay, sebabkan soalan ni dia bagi mass of nucleus, kita akan guna equation ZMP plus NMN minus mass of nucleus. Okay, back to the formula. ZMP, Z is the number of proton. So proton kita ada 2, mass of proton 1.007276 plus with number of neutron. So neutron kita ada 1, 2. So that's why here is 2 times with 1.008664 dan minus dengan mass of nucleus. Mass nucleus yang ni lah. Okay, so then we get mass defect 0.030377 U. Okay, sepatutnya kan. So bila kita add up yang ini, which is inilah, dia sepatutnya sama dengan mass single ni dengan mass nucleus tu. Tapi dia tak sama. Itulah yang kita panggil as mass defect. Okay, now we look at the binding energy. Binding energy tu define and use binding energy. So the definition of binding energy required to separate a nucleus into its individual proton and neutron. So okay, ni ada berapa ni? 1, 2, 3 neutron, 3 proton. So the combination of 3 proton and 3 neutron ni tadi, dia akan jadi nucleus. Okay, so dia ni ada binding energy yang ikat dia, yang pegang dia. So now kita nak separate kan, jadi 1, 2, 3, 4. Tadi 4 nucleus tu, dalam nucleus ada 4 neutron and 4 proton. So combination dia ni ada binding energy. Kita perlu binding energy untuk separate kan 4 atoms ni, 4 neutron dengan 4 proton, 3 neutron, 3 proton. Okay, so berapa banyak energy dia? That is we call as the binding energy. Or okay, daripada 1, 2, 3, 4 neutron and 3 proton. 3 proton. Kita nak combinekan single-single tu, combinekan dia. So kita kena ada energy jugalah nak combinekan dia. So ini adalah, that is actually the energy release masa kita nak combinekan dia. Bila kita combinekan dia, sebenarnya kita akan releasekan energy. So the energy we call as the binding energy. So here we have the formula for binding energy. Binding energy equal to delta MC square. Delta M is the mass defect. C square is the speed of light square. Then unit dia boleh jadi 2. Satu dalam MeV, another one is the other unit is joule. So tengok kat bawah ni, the larger the binding energy, the more strongly the nucleons are held together. So lagi kuatlah dia. Okay, so actually kita tengok ada 2 method to find binding energy. Satu unit dia dalam joule, satu lagi unit dia dalam MeV. So let's say question asks you to find the binding energy in MeV. So take note, bila dia tanya dia nak MeV, make sure our delta M must be in U. Tapi kalau the question asks you to find the binding energy with the unit of joule, make sure our delta M unit dia must be in kg. Okay, so lagi satu take note C dia. C sini kita guna speed of light, so C squared delta M E equal binding energy equal to delta M C square. So don't forget to square the value of C. Tapi kalau you guna MeV, C square ni kita just substitute with 931.5 MeV over U. U nanti kita boleh cancel. Okay, let delta M equal to 1U. So delta M kita 1U equal to 1.66 exponent negative 27. So if we are going to find the binding energy in joule, so E equal to delta M C square. Our delta M must be in kg. So dia dah bagi. So here in kg, C is 3 exponent 8. So don't forget here we have square. So dapatlah 1.49 exponent negative 10 joule. So one more is dia nak binding energy in unit MeV, delta MC square. So our delta M is 1, C square kita 931.5 MeV. So U cancel, so kita dapat binding energy dia 931.5 MeV. Ada dua unit dia. Okay. Okay, so for 11.1C, we look at the binding energy per nucleon. So the symbol for binding energy per nucleon is EB. EB stands for binding energy over A. A is the nucleon number. Okay, so first of all, we look at the definition of binding energy per nucleon. So binding energy per mass number, so which is A is the mass number or nucleon number. And the formula is delta MC square, which is delta MC square is actually the formula for the binding energy. And A is the nucleon number. Okay, what is binding energy per nucleon ni? So actually that is the average energy required to remove a nucleon from the nucleus. So it's a measure of the stability of the nucleus. So the greater number of binding energy per nucleon, so meaning dia lagi stable. So the larger the binding energy per nucleon, the greater the work done must be, the work must be done to remove the nucleon. So lagi besar number binding energy per nucleon, so we need more energy. Meaning we need more energy to split the neutron and proton at the nucleus. So and the unit for binding energy per nucleon is MeV per nucleon, or also joule per nucleon. Okay, now 11.1D, graph of binding energy per nucleon against nucleon number. So we have the graph, so let's sketch the graph. So here is the binding energy over A against nucleon number. Nucleon number, mass number, sama lah ya. So that is, the symbol is A. So let's look at the graph of the binding energy per nucleon number. So ni kita ada graph dia. So for H22 ni dia H2 only have one nucleon. So because of that, one nucleon je kan, so dia nak binding dengan siapa? So it has 0 binding energy. Next, if you look at the graph, the graph increase rapidly from H2, then dia pergi dekat helium 42. So helium 42, Next. Okay. Increase rapidly with increasing A for light nuclei and reaches at maximum at ferrum 56. So ferrum, mana satu ferrum? Okay, sini. Okay, so dekat ferrum ni, if you look at the binding energy per nucleon, so binding energy dia very large, which is 8 point something. So apa maksud dia? So kalau tengok sini, dia ada shaded area yang grey area ni. So dekat shaded area or grey area tu, it has more stable nucleus. So because for the ferrum 58, it has about 8.8 MeV per nucleon. So maksudnya dia very stable. Next, nuclei with nuclear number between 50 and 80 have the highest binding energy per nucleon and are more stable, which is dia punya binding energy per neutron is almost 9 mega electron volt. Next, look at here. So the value of binding energy per nucleon decreases slowly when A is greater than 82, where the nucleus less tightly bound as the nuclei get heavier. So tengok sini betul ke? So tengok kat sini dia decrease slowly daripada sini, and dia decrease. So bila dia decrease dekat situ, maksudnya dia jadi lagi less stable. So for heavy nuclei, A equal to 200 to 240 have binding energy per nucleon which are smaller, range between 7 to 7.8 MeV. Then these nuclei are unstable and radioactive. So uranium 238, tengok kat sini. The binding energy dia 7 point something je. So what happened here? Dekat sini uranium, kita tahu we are using uranium as the radioactive. So uranium very reactive. So dia unstable. Sebab tu uranium ni kita classify dia as the unstable and radioactive dia. Okay, so for 11.2, the radioactivity. So for 11.2, we have 5 learning outcome. Explain alpha, beta, and gamma decay. State and use decay law. dN over dt equal to negative lambda n. Next, define and determine activity. The symbol for activity is A and decay constant. So decay constant, this is the symbol for decay constant. Use n equal to n0 exponent negative lambda t, or A equal to a0 exponent negative lambda t. And the last one, define and use half-life. So half-life equal to ln 2 over lambda. So what is half-life? So we look after this. Okay, so 11.2, kita tengok yang first dulu, explain alpha, beta plus, beta minus, and gamma decay. So alpha is actually a helium nucleus. So helium is He42. So alpha ni also actually helium, sama lah. So kalau soalan tu as you mention, there is helium, so meaning there is helium 42. Or the symbol is alpha. So alpha is also refer to the helium 42. So helium 42 charge positive 2. Mass is 6.6466 exponent negative 27 kg. And its speed is 0.05 c. C here is speed of light. And the distance travel is between 2 and 4 cm. Okay, next kita ada beta. Beta, we have two type of beta. Beta minus and beta plus. So beta minus, the charge is negative. So beta plus, the charge is positive. So the difference is, dekat sini kita ada negative 1. So sini positive 1. Okay, so the other name for beta plus, we also call as the electron, negatron, samalah. So the symbol is E, 0, negative 1. So for beta plus, plus positive. So positive, positron. Positron also we call as anti-electron. The symbol is E, 0, negative 1. So mass for beta plus and beta minus is same, which is 9.11 exponent negative 31. Speed also same, 0.99 c. C is speed of light. And the distance traveled is between 2 and 2 to 3 meter. So now the number 4 is the gamma ray. Symbol gamma ray ni ya. So gamma ray actually that is photon. So meaning that is light. So bila light, so of course lah speed dia speed of light. Speed of light is 3 exponent 8 and it can distance about 500 meter. Okay, next. So for the ionization power, so alpha has strong ionization power if we compare to the beta and gamma. So gamma ni ionization power dia very low. Sikit je. So 10 pairs of ion per centimeter in air. So but for the alpha, 1 billion of pairs of ions per centimeter as they travel through the air. Next, we look at the penetration power. So penetration power for alpha weak. So we can stop the absorption by a sheet of paper because they lost their energy much more quickly. Tapi gamma ni it has strong penetration power. Higher levels can only be stopped couple of cm of block of lead or few meter thick concentrate. So maksudnya penetration power for gamma ni very strong. So effect of B is the magnetic field. So magnetic field ada effect tak dekat alpha? Yes, alpha positive charge. So beta pun dia ada charge kan? Beta plus, beta minus. Yes, boleh effect by the magnetic field. Tapi gamma ni tak boleh. Okay, then for the deflection in electric field, electric field, E for electric field. So, there is deflection to the negative plate for the alpha. Beta plus and beta minus pun ada deflection because beta plus is positive charge. So, beta plus they attracted to the negative, beta minus attracted to the positive plate. Then for the gamma, so gamma ni tak ada effect lah by the electric field. So no deflection sebab dia tak ada charge kan. Okay, so here is the diagram for the penetration power. Penetration power, effect of electric field, effect of magnet. Okay, so now we look at the alpha decay. So actually alpha decay usually happen to the heavier unstable nucleus where the number of nucleon greater than 82. So here is the example for the nuclear equation for the alpha decay. So alpha decay, alpha we refer to the helium 42. So that's why it's produce helium 42 dekat sini. Okay, so let's say we have X, A, Z. So A is the number of proton, Z is the nucleon number. So we have minus with the 4 and 2 for the helium. So dekat sini lah, this is our new nucleus. Okay, so example uranium 238 92. So then it happen alpha decay. For then it produce thorium 234 90. So another 4 become helium, another 2 become ini 4 2. So because kat sini minus and minus 4 minus 2. So 238 minus 4 we got 234. 92 minus 2 we got 90. This is the new daughter. Kita panggil anak dia lah, daughter 234 thorium. Next, so after alpha decay in the parent nucleus, the number of proton atomic number is Z has reduced by 7 and neutron number has reduced by 2. So, and the Nucleon number, which is mass number, Nucleon number sama lah ya. And the symbol is A, has reduced by 4. So, during the alpha decay, the energy is released. So, energy released in form of the kinetic energy of daughter and alpha particle. So, bila the energy release, so to get the energy is Q equal to delta MC square. Next, look at the beta decay. So, two lines. So, kita ada two lines dekat sini. Beta minus yang the blue color. Lepas tu yang black, that is the Nucleon number. So, the stability line, a gentle curve starting from the origin and of increasing gradient. So, the line n equal to Z, that is a straight line of gradient 1 through the origin. Yang ni, yang line hitam ni, that is the n equal to Z. Then, kita tengok description dia. So, for proton Z up to 20, from 0 to 20 here, n equal to Z is a straight line. So, dia sama je lah dengan beta minus tu. Okay, for all nuclei Z greater than 20, stable nuclei have more neutron. So, stable nuclei have more neutron. So, kita tengok kat sini lah, starting from 20 sini. The lines curve upward. So, dekat sini, line yang blue color ni. So, beta minus, beta plus. This is the example for beta minus and beta plus. So, let's say we have carbon 12, 6. So, they produce nitrogen 12, 7, which is the number of nucleon, number of proton tu. Dia ada increment dekat situ. From 6 to become 7. So, dia akan produce here E 0 negative 1, which is actually this is our beta minus. Beta minus must be paired with the anti-neutrino and also release energy. So, the energy is del Q equal to delta MC square. So, MB minus MA. MB tu dia punya parents lah, carbon 12, 6. MA is the mass of the daughter. So, it is produced when one of the neutron in the parent nucleus decay into proton, electron and anti-neutrino. Now, we look at the beta plus. So, beta plus, let's say we have nitrogen 13, 7. So, nitrogen tu dia jadi carbon 13, 6. And satu lagi, E01, which is this is the beta plus. Beta plus must be paired with the neutrino and also release energy. So, the energy release Q equal to delta MC square. So, delta M is the mass difference, MB minus MA. MB is the mass of the parent, nitrogen, daughter. MA is the mass of the daughter. Mass daughter is carbon. And also, ni ada 2Me ni. Okay. Time with C square. It is produced when one of the proton in the parent nucleus decay into neutron, positron and neutrino. Okay, for the gamma decay, this is the symbol for gamma decay. So, it occurs when an unstable nucleus release its energy in the form of high frequency EM wave called the gamma rays. In gamma ray, a photon, so it emit photon. Photon to actually that is the gamma decay when the excited nucleus changes from higher energy level state to a lower energy level. So the wavelength of the EM radiation are shorter than 10 exponent negative 10 meter. So, gamma ray photon are emitted when excited nucleus in an excited state make transition to a ground state. Okay, so ini because of the energy level. And equal to 2. Then they go to the ground state dia, and equal to 1. So this will happen when the nucleus decays into alpha or beta particle. So a nucleus that undergoes alpha or beta decay may also emit gamma ray. So possible juga for the alpha and beta decay, dia akan ada release juga gamma ray. Thus, gamma ray emission often associated with other type of decay. Okay, so this is the example. PU24094. So symbol star dekat sini meaning that is the unstable nucleus. Kita punya nucleus tu tak stable lah. So nak jadikan dia stable, so dia akan decay and produce gamma ray. So during the gamma decay, the mass number and the atomic number of the nucleus remains the same. Still same, but the difference is kita punya dia akan produce stable nucleus. So beza dia yang ada star dengan tak ada star. Yang tak ada star ni meaning dia dah stable. Okay, so this is the example. We have polonium 218, 84. So ada star kat atas ni, meaning dia tak stable. So dia produce produce decay. And tengok kat sini we have helium 42 and gamma ray. The second one, vanadium 234. They produce uranium 234, but different number here. So sini jadi this is beta minus, and also produce gamma ray. This yang ni unstable nucleus. So ni just produce gamma decay. Okay, next we look at the decay law. So decay law, state and use decay law, the n over dt equal to negative lambda n. So kita tengok dulu statement dia. Rate of decay or decay rate is directly proportional to the number of radioactive nuclei or atom and remaining in the source. So kena ingatlah, this is the decay law. So in form of the formula, so we get dn over dt equal to negative lambda n, which is actually is equal to the A here we call as activity. So negative sign means the number of nuclei represent decreases with time. So decay tu maksud dia reput. So maksudnya the number of nuclei tu dia akan decreases slowly. Tak kisah, it depends on the alpha ni lah. Alpha is the decay constant. So next, we're going to define and determine the activity and decay constant. So definition dia, activity is actually equal to rate of decay. dn over dt equal to A. So we also call as the disintegration per unit time by the radioactive nucleus. And the unit for the activity is becquerel, BQ, and the other unit is curie. 1 curie equal to 3.7 exponent 10 becquerel. 1 becquerel also equal to 1 decay per second. So dn dt, decay per second. Okay, now we look at the definition of decay constant. Here, this is the symbol for decay constant, defined as the probability of decay of a nucleus per unit time. So the larger the decay constant, the greater rate of decay. Different nuclei have different value of decay constant, and the unit for the decay constant is per second. Next, how to use the formula for the n. N is the number of nuclei, n naught is the number of nuclei, and initial. So we also have the equation for A stand for the activity. So kita disintegrate. disintegrate dn over n equal to negative lambda integrate with dt. So we integrate both sides. So kita dapat ln n over n naught equal to negative lambda t. So daripada situ kita dapat actually dia sama dengan n equal to n naught exponent negative lambda t. Ni lambda ni. So n is the nuclei remain at time t, n naught is nuclei when t is 0. Then for the A, this is how we relate activity and Nucleon number. A equal to negative lambda n and our n equal to n naught exponent negative lambda t. Kita substitute. Lastly we get A equal to A naught exponent negative lambda t. A is the activity when t and A naught is when t is 0. Next, kita nak define and use half-life. So here is the definition of half-life. The time required for the number of radioactive nuclei to decrease to half. So mesti decrease to half. So let's say initial dia 100. So how long is it about to decrease by half? So half from 100 is 50. So berapa lama ni nak ambil masa ni? So that one we call as the half-life. So the unit for the half-life are second. So unit also can be in minute, hour, day and years. So it depends on the unit of the decay constant. Then the formula, here is the formula for the half-life. T half-life equal to ln 2 over lambda. Okay, so this is the table for the half-life of some of the radioactive nuclei, and this value is constant and does not depend on the number of nuclei present. So uranium is still about 4.5 exponent 9 years to become half. Radon 22688, so 1.6 exponent 3 years. So tengok sini. So only 20 minutes to become half from the origin. Okay, so here we have the graph for n, which is n is number of remaining nucleus versus time t. So graph kita, graph curve, graph. So yang bawah ni represent the half-life. Half, 2 half-life, 3 half-life, 4 half-life. So the curve line, the red curve line here represent the n equal to number of nuclei remaining. So n equal to n naught exponent negative lambda t. So let's say our n here is 100. So become half from 100. Here is 50. So half from 50. Half from 50 is 25. Half from 25 is 12.5 and so on until n become 0. Okay, so that's all from our first and second subtopic 11.1 and 11.2. So that's all from me. Thank you. Assalamualaikum.